Lesson 8.2, Trigonometric Ratios. The objectives of the lesson are to find sine, cosine, and tangent of an acute angle, and use trigonometric ratios to find side lengths in right triangles and solve real-world problems. Your vocabulary words are trigonometric ratio, sine, cosine, and tangent. By the angle-angle similarity postulate, a right triangle with a given acute angle is similar in every other right triangle with the same acute angle measurement. So in this case, since we have three triangles, they're all right triangles marked in red, and one of the acute angles is 32 degrees, then triangle ABC, DEF, and XYZ, and the ratios of their sides, BC to AC, EF to DF, YZ to XZ, are all trigonometric ratios. A trigonometric ratio is the ratio of two sides of a right triangle. These are all similar triangles. By definition, the sine of an angle is the ratio of the length of the leg opposite the angle to the length of the hypotenuse. So looking at our figure, the sine of A, we have the opposite, so you could draw an arrow from A to the other side, that would be the opposite side, over the hypotenuse. Well, the hypotenuse is always the side across from the right angle. So the sine of A is A over C. The sine of B is B over C. The cosine of an angle is the ratio of the length of the leg adjacent to the angle. So it touches and helps form the angle to the length of the hypotenuse. So in cosine of A, we have B touching A. So we have B over the hypotenuse. And the cosine of B is A over C. If you stop for a minute and look, you'll notice that the sine of A is equal to the cosine of B, and the sine of B is equal to the cosine of A. This is because in a right triangle, A and B are complementary angles. The tangent of an angle is the ratio of the length of the leg opposite the angle to the length of the leg adjacent to the angle. So we take the opposite leg over the adjacent leg. So for A, it's opposite over adjacent. For B, it would be B over A. It's like you can take them complementary angles, their tangents will be reciprocals of each other. In trigonometry, the letter of the vertex of the angle is often used to represent the measure of that angle. For example, the sine of angle A is written as sine A. Let's look at an example of finding trig ratios. Write the trig ratio as a fraction and as a decimal rounded to the nearest hundredth. We want the sine of J. So we're looking at J. Sine is opposite over hypotenuse. So we look at J and we say opposite side is 60. Where's the right angle? Oh, it's over here at L. Opposite of that is the hypotenuse. So opposite of J over the hypotenuse would be 60 over 61. This rounds to 0.98. Let's look for the cosine now. The cosine is adjacent over hypotenuse. This side helps form angle J, so it's adjacent over the hypotenuse. So this time we have 11 over 61, or 0.18. Let's look at the tangent of K. Tangent is opposite over adjacent. So we're looking for 11 over 60, or 0.18. In special triangles, remember our 30, 60, 90 triangles and our 45, 45, 90 triangles? We can use a special right triangle to write cosine of 30 degrees as a fraction. We want to draw and label a 30, 60, 90 triangle. And we remember that the short side is s, the hypotenuse is 2s, and the other side is s square roots of 3. So the cosine of 30 degrees, cosine is adjacent over hypotenuse. So this would be s square roots of 3 over 2s. The s's will divide out, and I just have square root of 3 over 2. The hypotenuse is always the longest side of the right triangle. So the denominator of a sine or cosine ratio is always greater than the numerator. Therefore, the sine and cosine of an acute angle are always positive numbers, less than 1. Since the tangent of an acute angle is the ratio of the length of the legs, it can have any value greater than 0, but it must be greater than 0. No negative number there. Let's try using our calculator to find lengths of triangles when we don't have two sides. So if we want to find BC, the length of BC, and we see that we have a right triangle and one of the angles is 15 degrees. BC is adjacent to the given angle B, and we know AC, so we want to use the tangent ratio. So looking at the tangent ratio, we say that the tangent of B is the opposite leg over the adjacent leg, so AC over BC. Substitute the values we do have. The tangent of 15 degrees is 10.2 over BC. And you say, well, that's well and good, but how do I get BC now? Well, we multiply both sides by BC, then divide by the tangent of 15 using the tangent button on your calculator. BC equals 10.2 over tangent of 15 degrees. We simplify using our calculator, and we get that BC is about 38.07 feet. Let's try another one. We want to round to the nearest hundredth, and we want to find QR. So we're given the hypotenuse in this case and one angle. QR is opposite of our given angle. So we can use a hypotenuse and the opposite, which would be sine. So we want to write our ratio. Sine of P equals the opposite leg over the hypotenuse, which is QR over PR. Put in your values that you know. Sine of 63 degrees equals QR over 12.9. Once again, we want to multiply both sides times 12.9 and use the calculator. 12.9 times the sine of 63 degrees equals QR. Simplifying this, we get 11.49 centimeters. Let's find other lengths with trig ratios. Find the length and round it to the nearest hundredth, and this time we're looking for FD, which is the hypotenuse. We're given the angle F and the adjacent side to F, so we could use the cosine. Let's write the ratio. Cosine of F is the adjacent leg over the hypotenuse, which is EF over FD. Substitute our values in, and we get cosine of 39 degrees equals 20 over FD. Then we'll use the calculator and multiply both sides, dividing by cosine of 39, and we end up with FD is approximately 25.74 meters. Now you try. Make sure you complete the problem showing your work. and put them in your folder labeled 8.2 U tries. There's 2 pages, remember? And I'll see you in class.